Alright, in this video we're going to be working some linear algebra problems that have to do with mostly vector projection. So we're going to start by writing out the projection formula and the Gram-Schmidt algorithm. Okay, so the projection formula is that the projection of A onto B is going to equal A dotted with B divided by B dotted with B multiplied by vector B itself. Okay, and then the Gram-Schmidt algorithm, okay, we start with a set of vectors x1 through, xn. And so y1 equals x1. And then after that, the nth y is equal to the nth x minus where we project xn back onto all of the other ones. I'm realizing, I guess there might be enough room. Onto y1 minus the projection of xn onto y2 all the way up to the projection of xn onto all the y's that came before it, yn minus 1. Okay, that's the algorithm. But I don't think we're going to need to be getting into that on this problem set. So we wrote the algorithm, that'll be enough, at least for today. So compute the projection of u onto v. Glad. So that would be the projection of u onto v. That's going to equal u dotted with v divided by v dotted with v multiplied by vector v. Okay, so I'll start with that constant right here, this bit there. Put it in red parentheses, so u dotted with v is going to be 20 plus 15 is 35 over v dotted with v would be 16 and 9 is 25. Okay, so I'm going to go over here, 35 over 25 is going to be 7 divided by 5. Okay, and we're going to multiply v by 7 over 5. Okay, and you could do 1.4 if you wanted. I'm just going to say over here, okay, this is equal to 7/5 of 4 and 3, which is going to be 28 over 5 and 21 over 5. And for this next one, we're going to sketch the projection of A onto B. Okay, I'll just kind of put this, move it back over here. Because that's kind of what we're going to think about, is going back and making sure that we go down orthogonally to kind of the extension of B. So that would be, if this, that looks close enough. If that's a right angle, then this vector here, I'm drawing in blue, that would be the projection of A onto B. Okay, now this next one asks for the length of the projection. And now you could just find the projection and then compute the length of it, kind of the old-fashioned way. But this is one that there's kind of like a shorter formula for it. This is not a formula we've written down, so I might as well go through and like try to develop it again. But I'm thinking, maybe just draw a little diagram. That's B, this is A. I'm going to project A onto B. You've seen me do this before. Okay, it has to do with cosine, right? So this length of the projection here is going to be length of A cosine theta. But we also know that cosine theta is A dotted with, I'm just going to have to write it out. A dot B is length of A, length of B, cosine theta. Yeah, so that means that length of A cosine theta is going to be A dotted with B dotted divided by length of B. And that's what I kind of thought it was going to be because the way the formula works, but probably better to develop it if you're not sure, because it really didn't take that long. And I probably should have written, this whole vector out here. That was not A, this one's B, this one's A. All right. Okay, so then I'm going to just kind of use that formula over there in blue. So if I'm projecting y onto z, the length of that is going to be projection of y onto z's length is going to equal, what am I thinking? Oh yeah, y dotted with z divided by the length of z, because it's the one we're projecting onto. All right, so then y dotted with z is going to be 0, 0, 2, and 4 is 6. Be 6 over the length of z is going to be 1, 2, 2, 4. So that would be 16, and 4 is 20, 2 more is 20, or 4 more is 24, 25. Okay, so the square root of 25, that's 6 over 5. That's going to be the length of my projection. Right, now I'm computing the projection of C onto D. That'll, easy enough. That's going to equal C dot D divided by D dot D multiplied by vector D. All right, so C dotted with D is going to be 2 minus 3 is negative 1, minus 6 more would be negative 7, over D dotted with D would be, okay, 4, and 9 is 13, and 36 is 49. Nice, square root of 49 is 7. Wait, no, that was not what I wanted. I wanted D dotted with D, so that's going to actually be 49. Okay, I got a little ahead of myself. That's a Pythagorean quadruple. So it must have been, I don't know, maybe I used this for a different version of this problem set. So I multiplied D by negative 7 over 49, or negative 1/7, and that's going to be equal to negative 1/7. So negative 2 over 7, positive 3 over 7, and positive 6 over 7. All right, and our last problem here is number 5, and this is going to be as close as we come to the Gram-Schmidt algorithm here. We're going to find the projection of x onto the plane spanned by the vectors 1, 0, 1 and 0, 1, 1, and that's going to give us, I'm using blue for this type of thing, that's going to give us this vector. That's the projection of x onto that plane. And we would subtract the blue vector away from the one that's not on the plane to get that third orthogonal one. Okay. So, but I guess the first two are not necessarily orthogonal, so this is not exactly Gram-Schmidt, and I'm not necessarily assuming, pardon me, that angle right there in the plane is necessarily a right angle, because it's not. So, all right. What I'm going to do is I'm going to say, okay, well, what we're doing here, if we're projecting onto the plane spanned by these two vectors, we're going to have, this is kind of tough, but I think I know what to do. Pardon me while I make this diagram. Drag this over, right there. And then I'm going to see, that's going to be the tricky part, but actually I can just go over here and then move this guy up there. I'll show you. Okay, really what we're going to need is to find, I need a new color, to find these green vectors here, they're going to add up to the blue vector. And if you're having trouble visualizing that, I know I've been talking to some people about this is like kind of visualization of adding the vectors, and this is a program I can do that on. Okay, it's not going to take the arrow with it, but if I go over here and place that at the end of the previous one, that's what I'm thinking about when I'm thinking about vector addition. Okay, so I'm just going to put that right back there where it belongs, and okay, good. Okay, so the idea is that these green vectors, these are going to be the projections of x onto, the two vectors that span the plane. And so I'm going to say, I'm going to say projection of x onto, maybe I'll call them A and B. projection of x onto A and projection of x onto B. Is that a, okay. Let's say this one's A and that one's B. This is just kind of a general picture here. Then I will have, what was I feel like I had something else to say about this. Well, don't know what it would be. All right, so back to it. So projection of x onto A. Okay, that's going to equal x dotted with A divided by A dotted with A multiplied by vector A. So x dotted with A would be -1 plus 0 plus 1 what? Alright, I hate to do this, but the problem just really wouldn't make sense otherwise. So I'm just going to switch up those vectors A and B so that it does make sense. Okay, so x dotted with A, now I'm going to be back in business. -1 is -2, plus 1 back would be -1. Divided by A dotted with A is going to be 1, 2, 3. -1/3 of A. And that's going to equal -1/3, -1/3, -1/3. Okay, now I compute the projection of x onto B, and that's going to be x dotted with B divided by B dotted with B multiplied by vector B itself. Okay, and so that's going to be, okay, x dotted with B is going to be 1, -1 is 0, plus 1 is +1, divided by B dotted with B is going to be another 3, and so that'll be 1/3 of B. It's going to be -1/3, +1/3, +1/3. Okay, and so the projection, that blue vector that I've got, it's going to be projection of x onto the plane. You know, maybe I'll call this vector v, the thing I'm hoping to find eventually. That's going to be, you know, the two projections added together. So I'm going to say -1/3 plus -1/3 is -2/3. And then the other two components are going to be -1/3 plus 1/3 is going to be 0. So there's the projection right there. All right, so I think that's the end of the problem set. So that's going to be all for this video. Thanks for watching.